we start exercise 1.3. In which first sum we have to prove that root 5 is irrational. But we already proved in last lecture that is root 5 is irrational. So now we have to start with question 2 exercise 1.3. We have to prove that 3 plus 2 root 5 is irrational. Same proof. Let 3 plus 2 root 5 is rational. If it is rational, then it can be written as 3 plus 2 root 5 equals P upon Q or A by B, where HCF between P and Q is 1. That is, they are in their simplest form. P and Q are integers and Q is not equal to 0. We know that root 5 is irrational. Make it subject. So 2 root 5 equals P upon Q minus 3. Taking LCM. So P minus 3 Q upon Q. So we get 2 root 5 equals P minus 3 Q upon Q. Root 5 equals P minus 3Q upon 2Q. So now P is integer. Minus 3 Q is also integer. 2 Q is also integer. When we multiply any number with integer, it remains integer. Integer minus integer is also integer. Integer into multiplication, integer. So root 5 equals integer upon integer. Therefore root 5 equals rational. Therefore root 5 is what? Irrational. While right hand side is rational. Irrational equals rational, which is not possible. Irrational cannot be equal to rational number. And therefore our supposition 3 plus 2 root 5 rational is wrong. And we can say 3 plus 2 root 5 is irrational. Similar, question 3. Now we see question 3, exercise 1.3. Question 3, exercise 1.3, question 3, number 1. Prove that 1 upon root 2 is irrational. In 1 upon root 2, denominator is irrational, that is root 2. So first we have to rationalize the denominator, done in 9th standard. So multiply and divide with root 2. So now it becomes root 2 into 2, that is root 2 into root 2 is 2. So denominator rationalize. So now 1 upon root 2 can be written as root 2 by 2. So let root 2 by 2 is rational. If it is rational, then it can be written as P upon Q, where HCF between P and Q is 1. P and Q are integers and Q is not equal to 0. Therefore, root 2 equals 2P upon q. So root 2 equals 2 into integer. Q is also integer. So what we get? Root 2 equals integer upon integer. Root 2 is irrational. We know that. Integer upon integer, that is rational. And therefore our supposition, that is which is not possible. And therefore our supposition 1 upon root 2 is, 1 upon, that is root 2 by 2 is rational, is wrong. And therefore 1 upon root 2 is irrational. Question 3, number 2. We have to prove that 7 root 5 is irrational. So as usual, same proof. We can say first, same proof. So let 7 root 5 is rational. If 7 root 5 is rational, therefore it can be written as P by Q form, where GCD between P and Q1, P and Q are integers, Q is not equal to 0. Here root 5 is irrational, so make it subject. So root 5 equals P upon 7Q. Therefore root 5 equals P, that is integer, Q, that is 7Q, 7 into integer. Therefore root 5 equals integer upon integer. Root 5 is irrational. Integer by integer is rational. So irrational equals rational, which is not possible. And therefore we can say our supposition 7 root 5 is rational is wrong. And therefore 7 root 5 is irrational. Now question 3, number 3. We have to prove that number 3, 6 plus root 2 is irrational. So same proof again. Let 6 plus root 2 is rational. Therefore it can be written as 6 plus root 2 equals P upon Q. We know that root 2 is irrational. Make root 2 as a subject. So root 2 equals P upon Q minus 6. Therefore root 2 equals P minus 6Q upon Q. Therefore root 2 equals P, that is integer, minus 6 into integer upon Q is also integer. Therefore we get root 2 equals integer upon integer. Root 2, that is irrational, equals integer by integer rational, which is not possible. And therefore our supposition 6 plus root 2 is rational is wrong. And so we can say 6 plus root 2 is irrational. In this way we prove the numbers are irrational. One more extra sum. If we have to prove that Question, extra question now. Prove that root 6 plus say root 3 is irrational. That we have to prove. Now let root 6 plus root 3 is rational. If it is rational, so we can say root 6 plus root 3 equals P by Q. HCF between P and Q is 1. P and Q are integers. Q is not equal to 0. To remove the square root, taking square on both the sides. So root 6 plus root 3 the whole square equals P square upon Q square. Therefore, like A plus B whole square. So A square plus 2AB plus B square. So it is 6 plus 2 root 18 plus 3 equals a P square upon Q square. 6 plus 3 9 plus 2 root 18, that is 3 root 2, that is 9 2s are. Square root of 9 3, 2 remains same, that is root 2, equals a P square upon Q square. Therefore 9 3 2s are 6 root 2 equal P square upon Q square. Therefore 6 root 2 equals P square upon Q square minus 9. Therefore 6 root 2 equals P square minus 9Q square upon Q square. Therefore root 2 equals P square minus 9Q square upon 6Q square. Therefore root 2 integer minus 9 into integer upon 6 into integer. Therefore root 2 equals integer upon integer, and therefore root 2, that is irrational, integer upon integer is rational, which is not possible. And therefore our supposition root 6 plus root 3 is rational is wrong. And so we can say root 6 plus root 3 is irrational. So in this way we can prove the numbers are irrational. Now next topic, based on rational number. Now you know that rational number can be expressed in the form of P upon Q. So now P upon Q. So any rational number, say x, P upon Q, where GCD between P and Q is 1, P and Q are integers, and Q is not equal to 0. That is, P and Q are in their simplest form, no common factor other than 1, then we can say is a rational number. Now, one property. rational number is of two type. Number one is a terminating decimal expansion and another is non-terminating recurring decimals. Rational number are of two type. One is terminating decimal, one is non-terminating recurring numbers. What is terminating decimals? For example, 15 by 4. 3s are 12, remainder 3.0. 7s are 28, 2, 20, 4, 5s are 20, remainder 0. So 15 upon 4, 3.75. Terminating, that is remainder is 0. After 2 or 3 or 5 or 10 decimals, the remainder will be 0. Such number is called terminating decimal. Non-terminating recurring numbers. For example, 16 by 3. What happens? 16 by 3. 5s are 15, remainder 1. 0. 3s are 9. 3s are 9. Remainder 1, again 0. 3s are 9, 1. Again 0. 3s are 9, remainder 1, and so on. So 16 by 3 we can say 5.3333 ... meaning non-terminating. Infinite there is no ... It is finite. Here it is infinite. Also recurring, meaning repeated. In short form, you know that written as 5.3 bar. And many numbers are recurring, many are terminating decimals. Both are called rational numbers. Now, rational number denoted by P by Q, where P and Q are in their simplest form. Now we have to determine without long division whether given rational numbers are terminating decimal or non-terminating recurring number without using long division. So if the denominator, that is Q, written in the form of 2 raised to n, 5 raised to m. 2 raised to n, 5 raised to m, that is what? In the factors of, Q can be factor of either 2 or 5 or both, where n and m are non-negative integers, meaning maybe positive or 0. If the denominator, that is Q, can be written in the form of 2 raised to n, 5 raised to m, where n and m are non-negative integers, that is either positive numbers or 0, then we can say the given rational number is a terminating decimal expansion. If Q contain other than 2 or 5, then we can say it is a non-terminating recurring number. If Q can be written in the form of 2 or 5 or both, then it is a terminating decimal expansion. If it cannot be written in the form of 2 and 5 or other than 2 and 5, more factors are there in the denominator, then we can say it is a non-terminating recurring decimals. Here 15 by 4, we see the example. Both are in their simplest form, no other common factor between 15 and 4 except 1. So Q equals 4, nothing but 2 raised to 2, prime factorization. We can say 5 raised to 0. So 2 raised to n, value of n is 2, value of m is 0. So Q, that is denominator, can be written in the form of 2 and 5, and therefore it is a terminating decimal expansion. Another example we see in 16 by 3. what happened? Q equals 3, which is not in the form of 2 and 5. The prime factorization of 3 cannot be in the form of 2 and 5, and therefore it is a non-terminating recurring decimal. Now, also after determining whether it is terminating or non-terminating, we have to convert it in terminating decimal form without using long division. If it is non-terminating recurring, we don't have to convert in decimal form. But if it is a terminating decimal expansion, then we have to convert it in terminating decimal expansion without using long division. We already seen 15 by 4 is our rational number. First, you have to check whether they are in their simplest form or not. If not, you have to simplify first. One example, if given 10 by 50, common factor 10, cutting possible, it is 1 upon 5. If I say 63 by 70, then 7 9s are 7 10s are 9 by 10. First you have to simplify. Between 1 and 5 no common factor other than 1. Similarly between 9 and 10 GCD is 1. 15 by 4 no common factor other than 1. Denominator Q, that is 4, can be written in the form of 2 raised to 2, 5 raised to 0. So now we can say it is a terminating decimal expansion. Reason, Q can be written in the form of 2 raised to n, 5 raised to n. Now we have to convert it in terminating decimal expansion. We already seen answer is 3.75 using long division. Now without long division we have to convert it in terminating decimal expansion. Write again 15 by 4, it is 15 by 2 square. Now to convert it in terminating decimal expansion, power of 2 and 5 must be same. If not, you have to multiply and divide with the same power. Here 2 square, 5 raised to 0. So we required 5 square. जितना पावर 2 का होना चाहिए होगा उतना ही पावर 5 का होना चाहिए. So we have to multiply, divide with 5 square, 5 square. It is equals 15 into 25 upon 2 into 5 whole square. Powers are same, so base multiply 2 into 5. 15 into 25, it is 375 upon 5 to the 10 square. So 375 upon 100, decimal cut, answer 3.75, which is same as long division. But here we can do it without using long division. Now next exercise based on this principle. So exercise 1.4 we do it in next lecture.